This is Thasshwin Mathanlal from the University of Aberdeen, who recently got his doctorate and has been working on a fantastic project called PACKMAN.
Hi. So nice to meet you all, and I'm glad to present my work to the community of Aurorasaurus. So I'm Thasshwin. I'm doing my postdoc at University of Aberdeen. So I did my PhD in atmospheric sciences, and I have a background in space instrumentation. And I started my career as a manufacturing engineer, but I've now moved to science and working with space instrumentation. So PACKMAN, the name sounds really cool. It stands for Particle Counter K-Index Magnetic Anomaly. So I started working on this project during my master thesis. So it was just part of coursework. But then we found it really interesting to have an instrument that's portable to study space weather events. So I have been working on this project with my past colleagues, and my co-supervisor and supervisor, Professor Maripas Zorzano and Professor Javier Martin Torres. So before I proceed, I'd like to just give my background, a portfolio. So I did my bachelor's in manufacturing engineering in India, and then I did my dual master's in space science and technology from Lund University of Technology in Sweden and University of Würzburg in Germany. So, and I worked for some time as a research intern in France, and then right now I'm doing my postdoctoral fellow in planetary sciences at University of Aberdeen in Scotland. So pretty much the project that I have been working on with PACKMAN started in Luleå and also in Kiruna, northernmost part of Sweden, where it's quite famous for. It's called the Northern Lights town of Sweden. So that's where I started working on this project. So just show you some pictures. I took this map from Aurorasaurus map reporting about the auroral circle, and then we pretty much had very good auroras when I was working down in Kiruna and Luleå, and initially it was like wow, like I could see it every day right from my veranda, but then this was like really beautiful, and then I really wanted to see the scientific aspect behind it, and we worked with the Swedish Institute of Space Physics, so they have a campus in Kiruna, in northernmost part of Sweden. So it's where like a lot of researchers was conducted related to auroras and also space weather events. So this is just a slide. I think I'm just going to skip this slide because most of you here know the reason for how auroras are created, especially but our aspect of studying auroras was mostly from the ground-based observations, and not only limiting ourselves from ground-based observation, but also through stratospheric balloons and also through subsurface areas. For example, like we have a mine in the UK which has a sort of an environment that simulates subsurface environment for future Martian exploration. So we wanted to study the effect of magnetic field variation and particle counts right from at different latitudes, altitudes, and also covering different longitudes. So our approach was to have an open source autonomous instrument, completely low cost, a robust and scalable instrument that can be designed using commercial off-the-shelf components, so that it could be designed by anyone throughout the globe. So not just restricted to research institutes or to organizations, but to general public. So we have three important sensors in PACKMAN. So the particle counter to measure energetic particles, and triaxial flux gate magnetometers. So we went for flux gate magnetometers because they are commonly used for space applications, and they have very good sensitivity with respect to the Earth's magnetic field of plus or minus 80 microteslas. And we also have environmental sensors, which gives us a contextual information of what's the current environmental scenario around when we measure these parameters. So it basically consists of a temperature, pressure, humidity sensor, so pretty much it's those sensors, and then it's these two sensors which are primarily used for the space weather studies. So our approach was primarily using Arduinos because we find Arduinos are like more open source. It's quite easy to procure them throughout the globe, and they have very good literature. So it's very easy to have it for beginners and startups to design their own instrumentation. So we have magnetometers which we find from a partner in the Europe. So I have those links attached in a paper that we have published in HardwareX journal, where we have outlined the complete bit of materials that is needed, and also what's the program that is needed to run this instrument. So everything has been open source in the HardwareX journal. And we have like data also coming from Geiger counters, which we use it for measuring particle counts. And then we have the data from both magnetometers and Geiger counters put together along with the temperature sensors to have the data uploaded to a cloud server and also to internet. So we want to have like a cloud or network of instruments, like different nodes operating throughout the globe, and have the data pulled together into a central server, which is really good. I could see in Aurorasaurus, where you have like information that is posted by people, where you validate it, and you have it in a central cloud-based platform. So this is what we wanted to have with PACKMAN, but we have outlined this how we want to do it in the journal. But then we had our own local observations with different PACKMAN units that we had. So we had installed them quite in different locations. So we had them at 8 different locations. So right now we have one operating at the British Antarctic Survey at Antarctica at the Rotterdam station. And then we have one that we operated at the main campus in Luleå University of Technology in Kiruna in Sweden. So at 67° north, and also to the campus in Luleå, which is at 65 degrees. And we have one measurement instrument that runs in the Booty mine, which is a potash mine, which is like 1.1 kilometers deep in northeast of England. And we have one at University of Edinburgh, and we had 2 stratospheric balloon launches from Cordoba, Spain and Sweden, and we have one in Iceland. So pretty much the map shows like the current installation of PACKMAN units that we have around the globe. And so our approach, as I mentioned earlier, is to study space weather events not only from the surface, but also from below the surface and also at higher altitudes. So yeah, some of the pictures of PACKMAN. So we have developed two types of PACKMAN units. So one for surface-based measurements and one for stratospheric balloons. So we have PACKMAN B, which is meant for stratospheric balloon launches. So we had one launch from Cordoba, Spain, in Spain, and then one from Kiruna in the Arctic Circle. So one was a day flight and one was a night flight. And the data we could see that the diurnal variations of particle counts, and also we were able to study the Forza maximum phenomena with our instrument. So we also had twin units that operated ground at the surface at the same time when we had measurements taken up from the stratospheric balloons. And then we also have one in the mine, which is like in a more controlled environment. And some of the plots that we have from our instruments, like which we're running. So the plot on the top, you can see that we had our magnetic field measurements compared to that of an observatory in Heartland, which is an observatory from the British Geological Survey, which is close to our place. So we could see good correlation between the data that we get from our low-cost magnetometers with that of the instruments the state-of-the-art observatory. We could also compare our readings in the bottom left chart, where we could see the readings with a GOES 15 satellite magnetometer, and we could still see pretty good correlation with the data. And I think on 21 of November, we had a good G21 geomagnetic storm. So we could see respect to how the KP indices vary and the measurements that we got from our magnetometers. So these readings were taken from the mine 1.1 kilometers below. And we were also comparing our readings with the observatory in Kiruna. So yeah, I think this I took from the Aurorasaurus map from exactly on the date of 21st of November 2017, when we had a good G1 storm, and PACKMAN was able to detect the storm with respect to the KP indices, though operating at 1.1 kilometers in northeast of England. And we could see that the mine was providing us a very protected environment, because the sensors that we use in PACKMAN are low cost, and of course they have the impact of variation with temperature. So we wanted to have a very controlled temperature environment. So one of the reasons we wanted to have PACKMAN is to have it installed in a location which is like quite shielded away from anthropogenic activities, from people movement, and also in a very stable environment temperature. So we had installed PACKMAN for quite a long time. We had like 3 years of continuous data operating down in the mine. And from the data from the, we also had the particle detectors, which was mainly the dial counters. So the mine also provided us one good interface, because like we were quite shielded from the background natural radiation. So we were like 1.1 kilometers below the ground, and so we didn't have any sort of radon activities. So we could see the counts between 0 to 5 counts per minute, whereas on the surface it averages to around 15 to 20 counts per minute. So we could see the mine was providing us a natural shielded environment. And of course, down in the mine we have a dark matter research facility. So it's one of the facilities in the world where dark matter experiments are being conducted. And it was really good for us to also see if we could see any variation in counts with respect to sort of solar particle events. So we had 2 gyro counters operating down the mine. And most interesting results that we saw during was from the balloon launches. So one was a night-time operated balloon and the other was daytime. So we had two launches and we could see that at around this 25-kilometer altitude, we could see the Forza maximum phenomena. We could see the concentration of energetic charged particles at that particular altitude. And we could see the variation between daytime and nighttime, of course, because of the ionospheric changes. But this was really interesting because as a low-cost instrument that we had built with less than like $500 to $800, like we were able to show good results from this instrument, and we had published the results in a couple of in a journal and also in conference proceedings. So the entire roadmap of PACKMAN is to have it as an instrument for education and public awareness, because as of now we see that most of the instruments or for open source is related to general weather phenomena, but not to space weather. I see that a lot of people are not aware of space weather events. So we want to break this chain by creating a sort of education and public awareness to space weather events, and also to have like a comparison between Earth-based and Earth climate observation with respect to space weather, to see sort of any correlation that we can find between normal climatic changes with respect to space weather events. And we also wanted to have as a tool for real-time information for people who are impacted by space weather events, for example, with radio fields and also navigation, and also as a tool for trying to measure natural and artificial radiation sources. So like how they had the meltdown in Japan with respect to the nuclear reactors. So it's really good to have such a tool to make sure that we can differentiate between the natural sources and also artificial radiation sources. And later we also want to extend this network to the planetary data system, like how NASA uses. So we want to have like a scalable network that can be installed throughout the globe, and we can have sort of a common system with low-cost instrumentation and contributing to space weather studies. And these are the references to our papers that we have published through PACKMAN. And right now I'm still working with PACKMAN, like we're developing a more robust version of PACKMAN that could be useful for not only for like citizen science approach, but also for industries and people who can be impacted by space weather events. So thank you, and any questions I'll be happy to answer.
Can you guys hear me now?
Yep. Hello. Yeah.
You can actually hear me? Can you hear me?
Yes. Yes, we can hear you.
Oh, yay! Apologies for all of that. There's like 3 things to unmute. This is very interesting, and thank you very much. I'm sure there are some questions. While I have managed to unmute myself, I might as well ask one, which is, I was curious if you have, I guess 2 questions. One, since it's open source, which is fantastic, if there are any other people who've built their own that is, surprising or something like that, if you're aware of any of those. And then the second was whether you might have any conjugate locations, which is northern and southern hemisphere, the same points under the field line, sort of to attempt to take those observations.
Yeah. So thank you for your questions. Regarding the first question, there has been similar networks. I think it's called URAD. It was a system that was designed again to study space weather from an open source point of view. But our difference with respect to having URAD was mostly for trying from a radiation perspective, but we were more towards a geomagnetic perspective. So that's how we were different from an open source network of space weather studies. And respect to conjugate locations, we were successful to have installed one of our instruments through British Antarctic Survey to in Rothera Station in Antarctica. We still haven't got the data, but it would be really good for us because we want to compare the readings that we can find between northern hemisphere and the southern hemisphere. But still, we are waiting for the data.
Oh, great! Thank you.
You're welcome.
Laura, do you want to ask a question?
I was going to say, someone in the chat asked a question about Geiger counters. They never thought of Geiger counters before for space weather. and wanted to know how they work. Is it a particle counter?
Yeah. So Geiger counters, I mean, I wouldn't like one of the reasons why we wanted to go for a Geiger counter instead of using a particle detector was Geiger counters are quite easily available as open source, and also through eBay or through Amazon you can get a lot of Geiger counters. But we can have Geiger counters to measure space weather events very quite. I mean, that's a way to measure using coincidence detection. So we have two Geiger counters placed one above the other, and then we find the like a particle only when it's able to excite both the Geiger counters at the same time. So we use a sort of a coincidence system to make sure that it's a particle that's been originated by space weather events and not by local natural radiation, because the local radon activity cannot produce a particle of sufficient energy that cannot pass through both Geiger counters at the same time. So Geiger counters can be used for space weather events, but it can be made more sensitive by having a sort of a lead plate in the middle, because we can make sure that that's definitely a muon or any sort of secondary particle that has been produced by cosmic ray shower that can pass through both Geiger counters at the same time. But since we didn't have a sort of lead plates, because lead cannot be used as an open source, we just resorted just sticking with two Geiger counters and trying to see if both can be excited exactly at the same time.
Thank you.
Yeah.
I have a question. Thank you for your nice presentation. Yes,
Okay.
where exactly is PACKMAN device mounted? Is it a ground observation device, or can it also be mounted on rocket or balloon?
PACKMAN the circuitry is flexible to be operated both as well as on, like it can be a piggyback payload on balloons, or also even on sounding rockets. So our system is designed in such a way that we have our own onboard data logging units, power supply. So the hardware construction explains about the entire construction. So it need not have to be powered by like from the other payloads. So it just can be like a piggyback payload on any sort of stratospheric balloon launches, or even through rockets, the sounding rockets, definitely.
That's awesome. Yes. What other kind of application do you expect from PACKMAN?
The main reason for PACKMAN is like we had two sorts of approach. One, mainly for initially when we started the project, this was mostly for the complete open source and also to create like a network of stations. The main reason we find is because there's a missing data gap of information, especially with respect to studying space weather events at different latitudes and also at altitudes, and also with respect to diurnal variations. Because especially the Fox maximum phenomena, which has been recently studied, we still need more data to have more balloon launches that can take place at different parts of the time, at different latitudes and longitudes, so that we have like a lot of data with which we can see exactly how they change with respect to different seasons, or do they have any correlation with local climatic weather. So that's one of the reasons we wanted to have like a long-term data gap, and we want to make sure that we can have them like installed in all possible ways. Like any sort of launches, if there's going to be any stratospheric balloon launches, then we want to send PACKMAN because it's low cost, lightweight, and they can just send it along with their instruments.
Thank you.
Thank you. Can you hear me now?
Yep.
Oh, okay, good. Sorry, now my mic cut out for half of this, so I apologize. Thank you all for filling in. Liz wants to know, how did you come up with the PACKMAN theme? Are you a PACKMAN fan?
No, the PACKMAN name was given by my co-professor Maripas, so yeah, I didn't have the name for PACKMAN. So we wanted to actually bring particle and magnetic field measurements together in one name, and then we thought PACKMAN would be a good name, but we would run into issues because of copyright. So then we added a K because K index is good for Aurora studies. So we thought K index would be good to pitch both caps.
I love that. That's a great story. Thank you.
Yeah.
Thank you. Do we have any other questions for Thasshwin? Right. Well, thank you.
Actually.
Liz has them. Okay, I'm gonna turn it over to Liz.
Sorry. Yeah, no, sorry. I was trying to just put something in the chat, but things are just not working great today. But I noticed that your paper is in a journal called Hardware X, meaning like open source kinds of things. And I think that might be of interest to some of our people as well. So could you talk more about the experience with that journal? Is it a free journal? Just a little bit more about that, if you could.
Yeah, perfect, definitely. I even share my screen of the article that we are. Open my tab. So Hardware X is from Science Direct, and it's a completely open source free journal, so you don't need any subscription, and it's completely like free. And the best part of Hardware X journal, I would say, is because not only about it illustrates the construction of the instrument, but also they have a very good database where we upload all the even like videos of designing the instrument. But in our case, we were able to even upload the programs that is needed to run the microcontrollers. So it's like very easy for sort of like uh, making more multiple units. And we also have like the bill of materials. It also talks about the scientific aspect. So in the beginning, we just mentioned about why these sort of measurements are needed. And this part is can have block diagrams and with all the specification of the sensors that we use. So everything is completely open, transparent. So there's no hidden, like how do you say, hidden elements or something used. Everything is completely open source. And we also have the ability to have sort of the BOM, the bill of materials, to show exactly the supplier for each and every individual component that we have used in, what is the cost, what is the availability. So everything is completely available, open, right? The building instructions, the pictures, the schematics, the circuit, the wiring. So, and how we enclose it, and each and every command that we need to run to make sure that the instrument is functional. We have everything in the web page, in the journal.
I love it. And what is your hope for what citizen scientists will do with all of this going forward?
Um, so what I feel is, basic. For example, I was quite new to space weather because from my background, I was like mostly into manufacturing engineering. Then I started with my space instrumentation work, but still, space weather was something like which I didn't know of before. But then working with PACKMAN gave me the opportunity to see like with the data, and it's more better to study something rather than just going through textbooks to see how how sort of space weather events turn out. But with the data and with real time operation, we're able to know a lot about space weather events. So what I feel is like when students, or it could be from even, I've seen like some of the projects have been done by high school students. So it's not restricted only for researchers, but anyone who is interested or who have just heard about the name of space weather, I feel like they can use these sort of instruments that they can try to see if they can build them, or even schools can try to get funding for students to build such units, and that would give them a more practical approach to understand space weather events. So that's my feeling of trying to like spread the work of PACKMAN.
I love that. That's fantastic. Liz asks, do you have a favorite kind of northern lights? And I'd like to add to that, I know you're in Scotland right now. Have you been able to see them while you're there?
Aberdeen is a pretty cloudy place, so we don't not able to see a lot of northern lights. But
Oh,
we were lucky enough, like last year, to see a very glimpse of northern lights. But I was when I was in the Kiruna, it was like every day, and it was pretty nice. So I like the purple one that we used to go down away from the city to make sure that we are away from the pollution. So we used to go at minus 35 to 40 degrees Celsius, which was like super cold. And then we would just be on a frozen lake and try to capture some good photographs of auroras.
that's fantastic. We have several Aurora chasers on the call right now who I'm sure can relate to the cold weather. Um, Liz says this is very cool and innovative to share. She's hopeful that there are global opportunities to compare designs on magnetometers, especially. And Christina points out that Hardware X also published the design for ham size, low
Yeah,
cost personal space weather station system, which is called the Grape,
I was just
which is
looking at
really
the
cool.
paper. That was really nice. It's really
Yeah.
nice because we could like combine two such instruments together because from a radio perspective and from based on particle counts and magnetic field, things can be put together. We can try to correlate the data. So everything is like, and it's open source, so people can just put two units together also.
That's fantastic. I love the idea of collaboration. Before everybody got on, Thasshwin and I were talking about how important kind of the interdisciplinary, transdisciplinary approach to space weather is. And I love the fact that you're coming at this from engineering, and we have people at the call who are coming on this from, physics or education or space weather. Sometimes we have people who do space weather analysis, and we have folks who are aurora chasers, and sometimes we have historians, and it's really cool to get everybody in the same room to talk through. So thank you so much. Anybody have any other questions? Liz, do you have any other questions?
No, I don't have any other questions. Just thanks. I'm really glad we've been able to hear from you today. And I do actually have a short list in front of me of it's about 7 different designs for magnetometers, kind of low-cost magnetometers that are currently or recently in development. And I feel like there must be different use cases, and also just, I don't think we need to, I mean, this is all fantastic, but, going forward, maybe things either will be standardized, or there are standardized ways to compare the data as well that are important. And we don't, I think there are a lot of interesting science applications as well for very dense networks of magnetometers. So, and then also considering what's already happening, those will likely be many different designs and constantly evolving designs. So, some of them are on cell phones, some of them are Raspberry Pi, some of them are Arduino computer kind of boards, and some of them like the Personal Space Weather Station, some for high schools. It's pretty exciting time. And then also there's so many opportunities to combine with Aurora observations as well. So there are multiple designs for Aurora cameras that are doing time lapse. We have some folks in North Dakota that we work with, a group called the Live Aurora Network, and their camera design, their app design, which started out of Iceland. And then there's Jeremy in Ottawa, who's got his own Aurora camera in a box that can be set up. That's really great as well. So it is nice when you can see it and compare to the magnetometer signatures too. So all right, that's what I have to say. A long comment, but thank you so much.
Thank you.
Thank you.
This
is fantastic.
At the moment, we're also trying to work on a spin out, because with most of the sensors that we've developed, we're also trying to come up with cameras and that can work autonomously, so that we can try to set up in remote locations, and we have continuous data from all these sensors. So we're also working on that aspect also, because one of the drawbacks is when it comes into designing systems for open source. Then, for example, with the magnetometers, we face a concept like the problem of temperature changes, because temperature changes do affect the magnetic measurements. And we have to make sure that they are completely shielded, or they are installed under the ground, so that they have a constant temperature environment. So we are trying to come up with our new hardware changes, where we are trying to mitigate the effect of temperature changes, and so that we have very good quality data without having to bury them under the ground.
Yeah, for sure. The temperature changes are an issue, and maybe something that having multiple detectors in different places can help you. And so maybe there are ways that the data quality can be improved in the post-processing kind of stage when all those data are collected. I guess I do have one more question, which is, do you have any, how are you storing the data? Is it being stored in the cloud, or collaborating with a university, or, that can be also can fill up a lot of hard drives and those sorts of things quickly. So
at the moment, we have onboard data storage, and also we also have a cloud-based data storage. Depends on the place of installation. So we had quite some installations at remote locations where we were using 4G network for transmitting the data live to us. And for example, stratospheric balloons, it was pretty much stored on board the computers. And especially down in the mine, we had Ethernet connectivity. So PACKMAN is highly customizable. So depending upon the place of installation, we can try to have the data back to a central cloud server. So we didn't have a central server on our own that we made it public. So we just had data within our university, And but it's when in future it could be great that that could be one common entity like a web server where all the data can be pulled together. There was this program Kickstarter project called Raspberry Shake. So they had used a Raspberry Pis and a seismometer where they could see that either the data that get from the instrument could be made available to the common web server, or it could be that we use the data on our own. So we provide the same functionality for PACKMAN. So it depends upon the end user if they want to have the data put together into a central database, or it could be that they want to have the data private within them for analysis.
Thank you for mentioning that. The seismometer people also have that in common with us. That's a good solution. Sorry, Laura.
Oh, that's okay.
Go ahead.
I was just gonna say, I honestly, I hear a lot about data storage and how important it is and how challenging it can be, but I honestly struggle to kind of envision how much data is being generated by products like this. Do you have like a rough estimate in like terabytes, which is like something I can imagine?
For example, I would say in PACKMAN, we generate maximum of 2 megabytes per day. Depends upon the frequency. So we aim for like taking data every second. So
Okay,
not more than a couple of megabytes.
that's really cool. Thank you. That's something I can envision as I look at my my hard drive here. That's deep. Well, thank you so much. This has been really, really cool to find out more about, and I'm delighted to know more about PACKMAN. You have blown my mind about Geiger counters because I definitely just thought they were for looking for radium. Never thought that they could be used for space weather. This is amazing. So thank you so much.